Alright folks, I'm going to go through vector notes, and this is when we start talking about forces or velocity or momentums, anything that is a vector quantity that happens in two dimensions. So a lot of what we're looking at here maybe isn't directly applied to some of the physics laws we've learned about. Again, momentum and force velocities, Newton's laws. However, the application of how to use vectors in a physics way is something we definitely need practice with. So a lot of this is going to be just mathematical applications of vectors, and I'll show you guys later on how that applies to everything that we're learning. So to get started, if you guys take a look at your notes, one of the most common acronyms or the three trigonometry functions that you guys are going to have to use are going to be sine, cosine, and tangent. So a lot of what we do when we're dealing with two-dimensional motion or forces is you try to break things into right triangles. So if a vector is not pointed perfectly vertical or perfectly horizontal, and we're dealing with forces of gravity or applied forces, friction, whatever they may be, we need to use trigonometry to actually sum those forces up. Because it's very common that we can never add forces or subtract forces or vectors from each other unless they're collinear, which means that they're pointed in the same direction. So if you have vectors pointed in all different directions, oftentimes what we do is we break them into a horizontal and vertical component, or an x and a y, therefore of. So I'll kind of show you what the acronym, the SOHCAHTOA, stands for, which is printed in the box here. The SOH is trying to show that the sine of theta, and theta is a measurement or an angle equal to the opposite over the hypotenuse. And in terms of a right triangle, what's the hypotenuse, what's the opposite, what's adjacent? It's the hypotenuse itself is always considered the longest side of the triangle, which is normally some people would say the slanted side, although you don't want to always say that because the triangle could be oriented a lot of different ways. But it is in a right triangle always the longest side of the triangle. And your opposite side, your opposite and your adjacent side can change dependent on what corner or angle, theta, that you're measuring from. If this was our example, our theta is this lower left-hand angle or corner that we're measuring. So your opposite side would be the vertical or the y, and the adjacent side would be the x or the horizontal, because it is not the hypotenuse. We have the cosine function. So the cosine of theta is equal to adjacent over hypotenuse. So we'll abbreviate it like this, adjacent over hypotenuse. And again, if we're talking about this corner being theta, then your adjacent side is the horizontal and your hypotenuse is what we're calling r here. And then you have the tangent function. The tangent of theta is equal to opposite over adjacent. And again, if this is the theta that we're using, our opposite side is the vertical leg and the adjacent side is the horizontal leg. So you'll find there's a lot of different ways to describe all of these pieces and parts, and these equations here can all be manipulated. Think of them like a three-variable equation. Tangent of theta, tangent is a function, theta is actually a variable, so it's some angle that we're going to put in. Opposite and adjacent are both just variables, they're numbers. So we can multiply, put adjacent here, and solve for the opposite side. We can solve for the opposite side by moving, the adjacent side by moving tangent and adjacent around. You can multiply and divide, just knowing that all of these pieces can kind of stay as one. And it is also possible to solve for theta if you do the inverse of any of these functions. For example, if I want to figure out what theta is, if I don't know the angle and I do know the sides, I can do the inverse tangent of your opposite over your adjacent. Which, in terms of algebraic equations, when you're rearranging, you need to do an inverse or opposite operation to rearrange. The inverse of tangent is inverse tan. It's a tan to the -1. And on a calculator or a phone, you normally see the function as a sine or a tan or a cosine to the -1, which means the inverse thereof. So some of these equations applied in a little bit different form down here. Looking at this basic example of a right triangle, this is showing equations to solve for the unknowns, assuming that we're given a value for r and assuming that we're given a value for theta. To 20 degrees, and let's just say, for example, that the length of this hypotenuse, the magnitude of this r, was equal to 10. And we can call it meters, we can call it meters per second. I guess I'm not going to really worry about what that is at this point. But let's just say that you know that value and we know this value. If you wanted to solve for x, you would actually do r times the cosine of theta. Now remember, cosine is equal to adjacent over hypotenuse. So if this is our angle and we're doing adjacent divided by the hypotenuse of r in terms of cosine, all they've done here to solve for x, which is your adjacent, is they've multiplied both sides by the hypotenuse r. So they've basically taken this and moved it over here. Hypotenuse cosine theta equals adjacent. That's the same thing saying that this is our adjacent side and this is our hypotenuse. So you will see that they have different names. Generally speaking, in physics, we would call this the x, the y, and r as resultant. But again, they can be labeled a bunch of different ways dependent on what we're dealing with. If we're dealing with, again, forces, momentum, or velocity, those will all have different names. The thing to try to follow here is the overall concept of how to apply these mathematical workings. So if I was going to try to solve for this as an actual value of x, I would plug in the numbers that I got into the equation. If r is equal to 10, and then we do the cosine of theta, which in this situation is 20 degrees, I could plug that value in, making sure if you are using a calculator for the sine, cosine, tangent, you got to make sure that everything's in degrees. There's a radian function and there's a degree button. So if you're changing that on your phone, if it's a Texas Instrument, you know, a TI-80 something, there'll be a button that says mode. You can hit mode and it will say DEG or RAD, DEG being degrees and RAD being radians. So whatever device you have, you may want to make sure that's in the right setting. One way to check that is if you hit the tangent button in 45 or 45 tan, depending on your operating system or your device. The tangent of 45 should be equal to 1. So if you want to check that it's in degrees or in the proper setting, check the tangent of 45 and make sure that it's equal to 1. So if I do this, if it's a TI-80 instrument, I'll do 10 times cosine of 20. And I get 9.36. Sorry, 9.39 approximately. Whatever that, if we're measuring in meters or kilometers per second or whatever it happens to be. Then for figuring out our value for y, y is over here. So this is our vertical leg, this is r times the sine of theta. And again, if we take a look at the sine function, they did nothing more than just rearrange. If this is our angle, sine is equal to opposite over the hypotenuse, so our y over our r. We're trying to solve for y, which is our opposite, so they multiply both sides by the hypotenuse, aka r, and we have r times the sine of theta will equal our opposite side. So this is all still holding true, it's just the variables that we're using are a little bit different. So if I want to try to figure out the value for y, which is over here, again, our opposite side, because theta is here, opposite adjacent hypotenuse, I'm going to do the magnitude of the resultant, which is 10, and I'm going to multiply it by the sine of theta, which is 20 degrees. And we should find that this value here is going to be quite a bit smaller than this side. Remember, if this angle is 20, this side's in essence going to be quite a bit smaller. If it was a 45-degree angle, each of those sides would have to be equal lengths, hence why the tangent of 45 is equal to 1. So, plug in these values here, let's see what we get. I'll do 10 times the sine of 20 degrees. And this gives me about 3.42 as my value for that. Okay? If we were to try to find the resultant, this looks a lot like Pythagorean's theorem. Assuming that we didn't know maybe the magnitude of this side, maybe we only knew the length of the x, or maybe only the length of the y. If you guys were trying to find the length of the hypotenuse, if you think of a squared plus b squared equals c squared, they in essence just solved for c. So r squared would equal x squared plus y squared, but if we're trying to find for the value of r, you'd have to square root both sides. So if I did not know what this was, if this was 7 and this was 3, we would have to square 7 and square 3. Once we get the sum of all those, we'll square root it, and that would tell us the length of our hypotenuse. And then in essence, to try to find slope, which is your rise over your run or your y over your x. You in essence can just take the tangent of whatever that angle is. So if I wanted to figure out the slope of this, what is my rise over my run? Written in terms of, say, a percentage or a decimal, if I got the value of 342 and 9.39, my rise over my run is kind of a goofy looking number. It's not some nice, 1 over 4 or 2 over 3. But again, those can all be put in terms of decimals, which we will apply a lot of this as we go on. So that's just a basic introduction as to how you can use sine, cosine, and tangent to try to solve right triangles. So, first example. They give us a right triangle diagram, looks kind of like this, and they say to find the x and the y values if r, the resultant, is equal to 10 meters and our theta is equal to 25. So they're going to tell us that this r here is equal to 10 meters, and they're going to ask us for x, and they're going to ask us for y. So these two things are unknown, but they do tell us that the angle over here in the corner is equal to 25 degrees. Solve from there. So without thinking too complex about sine, cosine, and tangent, we could stick to our equations from up above, and we can know that x, which is our horizontal leg, is equal to the resultant of 10 multiplied by the cosine of theta, and our y, again, sticking to the equations from up above, is equal to r times the sine of theta. If we plug in our unknowns, our variables that they give us, let's see, we got r is equal to 10, and we got the cosine of 25 degrees. And here we got r equal to 10 times the sine of 25 degrees. Plug each of these into our calculator and see what we get. This gives me 4.23 meters as the cosine of 25, which is equal to about 9.06 meters. Looks something like that. Next example, this says they want us to try to find r, so we do not know what r is. So r is the unknown here, and they tell us that x is equal to 5, and they tell us that y is equal to 10. So we do not know theta, and we do not know r, so things are kind of given to us in an opposite order. So what you got to think about here a little bit is, what do we have? You do know opposite, you do know adjacent. Assuming that theta is in this corner, you have the ability or the liberty to decide what corner is really going to be theta, but as the previous examples have shown, our theta has been the measurement from horizontal, which is most commonly that. And if I do know opposite and I do know adjacent, the one function that stands out in mind to me is the O over A, which is your tangent function. So I'm going to start out by saying that the tangent of theta is equal to opposite over adjacent, which in this situation is y over x. If these two are known, and the one that we're trying to find out is theta, I can just do the inverse tangent of y over x in order to figure out theta. And that's what I'm going to do to figure this portion of it out. So I'm going to do the inverse tangent of my y, which is 10, over my x of 5. So I'm really doing the inverse tangent of 2. So I do inverse tangent of 2, and this gives me about 63.4 degrees, which will be your value for theta. And if I'm trying to find my r, which is the unknown length over here, again, you can kind of stick to using Pythagorean's theorem. We know that this side squared plus this side squared will equal that side squared. So if that's the case, I would have 5 squared plus 10 squared would equal, in essence, r squared. If I solve for r, you need to square root both sides, which will look more like this, and then my square goes away here, so I'm just left with r equals that. So figure out what we got. We got 5 times 5, which is 25. We got 10 times 10, which is 100. So we're really taking the square root of 125. That in itself could be your correct answer, but we can also check and see what the square root of 125 is. It is not a perfect square, but it's definitely more than the square root of 11, which is 121, and it's less than the square root of 12, which is 144. It's very close, gives me approximately 11.1. And again, if we're measuring in meters or whatever the variables happen to be, just how it would work out. Next example here, they're giving us the magnitude of a vector, and you'll see that here it's labeled a little bit differently. They're just going to call this vector A, and they're going to tell us what the magnitude of the vector is, and they're going to tell us what the theta is from horizontal. Then you're supposed to try to figure out what is the component of x and what is the component of y. So this is pretty common as to how you should try to analyze and set up the vectors in the world of physics. They're going to say there's a force pointed in this given direction or a distance in this given direction, find the horizontal and the vertical legs of it. So here's the component of vector A. It has a magnitude, so they talk the first part, the magnitude, so how long is the vector itself, and then they tell you what direction it's pointed. So remember, vectors are made of two things, a magnitude and a direction. We're going to call vector A. It has a magnitude of 5 meters. And it's theta here, which they're talking about in this example. They're assuming that theta is from the horizontal, which it will not always be, but in this situation it is. So there's a horizontal leg that goes this way and a vertical leg that goes this way. So summing some of these up, you'll find that we have vector A as a resultant we know is equal to 5, but we're also going to have components of A, which we'll call A of x and say A of y. Now, if they were generically labeled, we could call the resultant vector R of x, R of y. Either way, we're just trying to find the horizontal and the vertical component of these two. So we don't know what these are right now, but we're going to be able to figure them out. So I'm going to draw this and this, so I'm going to have my R of y here and my R of x here. Now, according to some of our equations from before, if I have theta and I have the hypotenuse, if I want to find, let's say, R of x, which is the adjacent, if I have adjacent and hypotenuse, I'm going to be thinking of the acronym CAH, which means the cosine of theta is equal to adjacent over my hypotenuse. Why is that important? Because my adjacent is the unknown and my hypotenuse is known. So if I'm trying to solve for this, I'm just going to basically multiply both sides by h. So h cosine theta will equal my adjacent side. So the way that this is written maybe doesn't match the variables that we have here, but the whole concept is the same. We're trying to solve for this, which is our adjacent side to theta. So if I'm trying to find my A of x, I know that I'm going to have the hypotenuse, which is 5 meters, and I'm going to multiply it by the cosine of 30 degrees. There's lots of different variables here, I will agree, but it's still the same concept. This is our horizontal leg, this is our hypotenuse, and then the cosine of 30. When I'm trying to find the vertical leg, I'm dealing with, if this is the theta or the angle, my opposite side is R of x and my adjacent side, my opposite side is R of y, my adjacent side is R of x, and my hypotenuse is 5. So for this one, I'm thinking opposite and hypotenuse. So in terms of our acronyms, I'm thinking the sine function. So if I do the sine of theta, I know it's equal to O over h. If you multiply both sides by h, you got h times the sine of theta is equal to O. So again, how does this relate to this? If theta is here, my opposite side is over here, which right now is my unknown. This is the same as R of y. And my hypotenuse is here, which is known as 5. So if I plug that in and I want to try to solve, I know I'm doing 5 times the sine of 30 degrees for this value. And now all we got to do is plug in and solve for the unknown. So I got 5 cosine 30. This gives me about 4.33. And down here I got 5 times the sine of 30, which is equal to approximately 2.5. So if I was going to be labeling my x component, here I have 4.33, and for my R of y I have 2.5. We know that the units that we measured here were were given to us in meters, so that's what we're going to stick with. Next example, they're basically asking us to do the same thing, however, they do not give us the angle from horizontal. In this situation, they give us an angle from the vertical or the y-axis. Now, again, in physics, when problems are written, they can be written in a whole bunch of different ways as to where is this angle measured from. Is it measured from north? Is it 360-degree bearing? Is it off of the vertical? Is it off the horizontal? So we need to pay really close attention to where to place these values. And then when you go to draw the horizontal and vertical legs or find the resultants, how do they apply? So in this example, they just say that there is some vector A and it has a magnitude, so I'm going to label this vector A, has a magnitude of 10 newtons, so they're dealing with a force going off kind of in this direction, and they say it makes an angle of 55 degrees with the y-axis, which is the vertical axis. So in this situation, we have a couple of choices. You could draw a right triangle in this fashion right here, and we can call the x and the y, and this being theta, we could call this side our opposite, we could call this side our adjacent. Perfectly fine, nothing wrong with that at all. If you want to stick to your methods that we have been using, and you want your vertical leg here and your horizontal leg here, and you want to be using this angle over here, calling that theta, you can certainly do that. However, the thing that would be true is, in terms of geometry, your angle here would be the same as your angle here. So here's 55 and 55 degrees. And if we're talking about our other angle, we're looking at a 35-degree angle down here. Knowing that the sum of these two angles has to equal 90 degrees, this leaves me with 35 degrees here. So now this can be my x and this can be my y. So either one of these setups will be okay. If your theta is here, this is my opposite and this is my adjacent. If this is my theta here, this is my opposite and this is my adjacent. So it'll change the function that you're going to be using. Here I can do 10 times the sine of 35 will equal y. Here I can do 10 times the cosine of 35 will equal x. If I'm on the other side, I got 10 times the cosine of 55 is equaling x, and 10 times the sine of 55 is equaling y. So I'll solve it this way. I guess either one's appropriate. So let's just say I'm trying to solve for x. Again, x is the, if I'm using 35 degrees as my theta, x is the adjacent, this is opposite, this is my a, x is the a, and 10 is the h. So a over h is the cosine function. So I know here I'm going to have 10 times the cosine of 35 degrees. And y would be equal to 10 times the sine of 35. So we can plug in the values here if you want to check some of your work as you follow along. 8.19, and then I got 5.74 if I round it. And again, these will be labeled in newtons. It's always a decent idea to at least kind of check to make sure your answers make relative sense. If your hypotenuse is 10, we know that these two legs have to be less than 10. And out of the two legs, whatever one, if the angle is less than 45 and you're on the opposite end of that, for example y, I know that this value is going to be smaller than this value. Now, precisely just making guesses, you can't really guess, but once you've calculated it, just know that, okay, well this is on the shorter side of 45 and this side is, remember, 55 degrees now. So the side opposite of that 55 has to be a longer side because it's a wider angle, so it's going to create a longer side on the opposite leg of that triangle. So, directions of vectors. As we've seen in the previous two examples, sometimes they measure degrees from horizontal, sometimes they measure degrees from vertical. These are some examples of various ways we can measure directions that vectors are pointed. The magnitude part, pretty easy. They just give you a number, but the angles, that's where it kind of throws us a little bit of a curveball. We got to try to figure them out. So first example, here's a vector E. In the diagram or the picture, they show theta to be 25 degrees, assuming that the triangle is drawn, this way. We got 25 degrees here, our y would be our opposite, our x would be our adjacent if we knew what E was. So we can say that E is equal to, they give us a value of 15 meters. It's 25 degrees north of east if we're using a 360 degree bearing, and This is pretty common also in terms of navigation. So north on the piece of paper is normally considered to the top, east to the right, south straight down, and west to the left. So we go clockwise around as the angles get larger. So oftentimes our playing field is somewhere over here if arrows are pointed like up and to the right. So we can say that this is 25 degrees north of east, so above the horizontal is one way to measure that, or they would just say that it's 65 degrees east of north, so north being here, 65 degrees toward the east direction. And more commonly, what I prefer, and is if you get further along in physics, they will just give you a bearing from north. So this would be considered a bearing. So from north, you rotate 65 degrees and then you draw your triangle. Because in essence what they're showing is if you had 0 degrees here and this was straight north, you would go 65 degrees clockwise to rotate it into that position. Okay? Now, everything in quadrant 1, the numbers seem to work out pretty easy. There's not a lot of crazy things to add and subtract. But if you get things that go beyond 180, 270, and so forth, for example, vector G, we have 0 degrees here, we have 90 degrees here, I have 180 degrees down here, 270 degrees here, and the first indication for theta that they give me is this 25 degrees. Now, when we're dealing with solving right triangles, we in essence really only care about what one of these angles inside of the triangle is. Well, there's a lot of other ways to measure where this is pointed. Again, if we are talking about coordinates from horizontal, so this says, first example is 25 degrees south of west. Well, west is straight this way, 270. So again, maybe from the horizontal, they'd say this is 25 degrees below the horizontal, or 25 degrees south of west, with west being this way. That application is great if we're drawing out the triangle and want to know that theta is 25 degrees and we can solve for x and y. Another way they could look at it is, all right, well, let's say it's 65 degrees west of south. And another way they might state that is it's 65 degrees from the vertical, with the vertical being your 180 degrees. It's swept out 65 degrees from this direction, which you could create another triangle here, and you could still solve for your x and y components, but your value for theta and your opposite and adjacent sides now are flipped from what they would be here. Or we talk about it in terms of a bearing again, which is all the way from north. So if north is here, they're flipping it all the way around, like how far did we go, we're pointed in what direction. This is 245 degrees all the way from north. Remember, 180 is here, and you add your additional 65 to get you to the 245 degrees. Pros and cons of each: when they give you bearings north or south of the horizontal, or east or west of the vertical, it's normally giving you a theta that's useful to plug into your triangle. When we're dealing with bearings, the thing that's good about a bearing is there's no arguing where the angle is or goes. Out of a two-dimensional plane, we're only dealing with 2 dimensions for now. We won't get into 3, but maybe later. This is definitive on where it's pointed. 25 degrees could be south of west, north of west, east of north, west of north, north of east, south of east, east of south, or west of south. All of the above. It could be labeled all those different ways. But 245 degrees as a bearing is just one direction, one location. And then from there you can do your application of trigonometry to figure out the x and y components. Now we can talk about adding and subtracting vectors, which is really what we end up having to do when there's more than one force acting on an item. The thing about adding vectors, when they're pointed in what they called, when vectors are considered to be collinear, meaning that they're pointed in the same direction and on the same plane, they happen to be just added. I mean, their magnitudes, if someone's pulling straight east and another person is pulling straight east or west, if it's in a straight line like a tug of war, 2 people pulling on the same rope, you just add the magnitudes together. One person pulls with 5, another pulls with 10, their magnitude's 15. Now, most vectors are not given to you in that simple of a fashion. You normally need to find the components and then do that. You find the horizontal and then find the vertical and add those together and then redraw. So I'll show you how all of that works. The first examples here are just adding and subtracting collinear vectors, so they're all pointed in the same direction. How does it work? Pretty simple. you got a positive vector and a positive vector, both pointed to the right or straight east or 90 degrees, however you want to state that. They're both positive. One's 3 meters, one's 2 meters. You literally just translate this one up and you add them tip to tail if A is the first one and B is the second one. I'm just going to put it right in line. This is 2 more meters, so the sum of this whole thing, once you've added it together, is just 5 meters. And they may call this vector B. They may show this as A plus B equals C, or in this situation they're saying R. What is the resultant vector of A plus B? What does it equal? Well, they're both positive. 3 plus 2 is 5. Second situation, we got 2 more collinear. They're still on the same line, even though they're not pointed in the same direction. We got a positive 3 and a negative 2. You still add these together the same way. I can go tip to the tail of this one and then look at what's left over. My resultant R is really here, which if I want to look at it mathematically, you know, A plus B equals R. My A was 3 and my B was negative 2, so my R is just going to be equal to 1. So I know that this is 1, still pointed to the right, so if I added these two together, my resultant vector would just be 1 meter to the right. This would be equal to R. That's all that's left over is the 1 meter. Examples down below show the exact same thing. Here's my 5 meter vector. Here's my 1 meter vector. So then the question ends up being, what do we do with vectors that are not collinear, meaning that they're not pointed in the same direction? How do we add those together and figure out what we got? All right, well, here's our example. They're going to say here that vector A and vector B are pointed in different directions. Vector A is going to be pointed in the horizontal direction, so we can say that, you know, vector A is equal to 2 meters, and I'm going to just give it a direction of, let's just say, 0 degrees. So this one's going to be pointed straight north. And I'm going to say that vector B is equal to 5 meters, and I'm going to say it's at 90 degrees. So one's pointed straight up and one's pointed straight east, so north and east. So if that's the case, I know I have basically a 5 here and I have a 2 here. And then they're asking us to try to find R. So what is R? What is the resultant here? Well, if we're going to do that, that's when the trigonometry comes in and we need to try to figure out what those pieces are. So you can use Pythagorean's theorem once you have the horizontal and the vertical figured out. Again, I know that R squared would be equal to 5 squared plus 2 squared. And if I want to take the square root of both sides, I know that R would be equal to the square root of 5 squared plus 2 squared. And that puts R being equal to the square root of 25 plus 4, which really tells me that R is equal to the square root of 29. And again, 29 is not a perfect square. However, we can still figure out the value of it. It's larger than 5 and less than 6. So this one gives me 5.39 approximately. And again, if this is meters, that's what we end up with. More methods for adding vectors. There are geometric ways to add vectors. For example, if we have a coordinate grid or some way that vectors can just be locked in place, you can physically move or add vectors tip to tail as long as the magnitudes and the bearings stay in the direction they're facing. If you can just slide them around on, say, a two-dimensional plane. So this is a little bit more conceptual, a little bit less math involved, which is kind of nice. So I'll show you the application of this. So remember, tip to tail, or heel to toe, sometimes they may say, is the most common way to do this. So they're going to try to find vector D, which is E plus F. So E is just pointed straight to the east. We don't know, who cares of the magnitude at this point. We could say it's equal to 5. And F is kind of at an angle. We don't really know what the angle is. All they're doing is they're translating this onto E. So from the tip of that to the tail of this, and they draw it out. So here's the direction, here's the direction. If this was fully completed, I could sum up all the horizontal and all the vertical components of this to also figure out what D is. But it follows the same rules. We started here and we ended here. And in essence, that's what we're trying to figure out in terms of vectors, is what is the sum of your x and what is the sum of your y. For the next one, we got A going kind of, up and to the right, and maybe this is at a bearing of, 50 degrees or 45 degrees, and B is kind of pointed down and to the right, which maybe is at a bearing of, 120 or 130, and we need to add them together, so you literally just go tip to tail, so we translate this down, goes up and goes down, and what is my resultant? If this is A and this is B, my resultant C is actually right over here. Just add them up tip to tail. What happens when you subtract vectors? It's the same as when they're collinear. You just flip the sign on whichever one is being subtracted. So if A is going this way and B was going this way, when you subtract it, you literally just flip the sign. So if this is a negative B, instead of the magnitude going this way, it goes that way. So I just take this and flip it 180 degrees. So here's vector A going this way. Our original positive vector B would have been going off here, but since it's a negative, we just point it in that direction and sum them up. Again, we'll get to a point where we're adding using your x and y components, and basically all we did with B is we made the x a negative value going to the left, and we made the y a positive value going up, because it originally started with a negative and a positive for your y and your x. So those signs just got flipped, and we can draw the resultant as is. So the next thing we're going to take a look at is adding vectors by components. So they're basically summarizing the horizontal and vertical components of two different vectors and then just adding them together to get your resultant. So in this example here, they kind of have most of the work, trigonometry portion done for you. This is more kind of a concept just by looking at it. But they give us our first vector, A of r, and they tell us that the horizontally the x component, A of x, is equal to 12, and our vertical component, or A of y, is equal to 9. And then they show that vector B, the resultant, is going in this direction somewhere. They just say that the horizontal component is equal to 4 and the vertical component is equal to 15. So again, remember, we can add vectors when they're collinear, pointed in the same direction. For example, my two x's, the A of x and B of x, can be added straight together going to the right, and my vertical components, B of y and A of y, going straight up, can be added together. So all they did to add vector A plus vector B is they took A of x plus B of x across the bottom, which is going this way. And if I was going to redraw this as a new vector, it just means that C of x, so A plus B, if I added my x's together, my C of x would be equal to 12 plus 4, so that would give me 16. So I could go 16 to the right. And then the vertical component, my A of y and B of y, we have 15 and 9, so that gives us 24. So going upward like this, which we could call C of y, would be equal to 24. And I could draw my new vector C here, C of r going that direction. So it's drawn out with the components. If we wanted to find theta, or we wanted to find the magnitude of r, we could, because we have two sides. And if you have two sides or an angle on a side, you should be able to figure the rest of it up. So now, putting it all together, this last portion here, they're basically giving you a bunch of different vectors. Some are pointed in positive directions, and some are going to be pointed in negative directions. Either way, we still need to find a way to sum up the magnitude of all the x's and all the y's so we can add all these vectors together. Because again, when there's only two vectors, it maybe isn't so bad, but when you have 3 or 4 or maybe even more vectors added, basically what we try to do is, list the vectors. These are all given in degrees from north, so the actual degree or angle that they give you is not always directly helpful in figuring out the right triangle, getting the x and y components. So you have to do some reasoning or deductive thought there to figure it out. We got to make a sketch of what our right triangle looks like so we can apply our sine, cosine, and tangent functions. And figuring out the magnitude of these should be the same as the magnitude of the vector, so that in essence would be the hypotenuse of whatever triangle that you draw. Our degrees from horizontal would be the theta that we're going to be using with our trig functions. Again, this could be above or below the horizontal. And then what we're really trying to get after is the x and the y component. So similar to what we just did above, if we know all the x's and we know all the y's, again positive and negatives, we can just add them up at the end and draw our new resultant vector. So here's the first vector. Vector A says it has a magnitude of 10 and it is 30 degrees from north. So the only thing I know for certain is the magnitude of this is equal to 10. the degree from horizontal is not the same as the degree from north. Remember, 0 degrees is straight up and down, it's rotated 30 degrees this way, so I know that the triangle is going to look something like this, with the resultant, we know that this is equal to 10. What we really want to figure out here is we want to figure out theta, and then we're going to try to figure out the x and the y. So if it's rotated 30 degrees from north, that means my theta here is 60 degrees from the horizontal. So I'm going to be writing that in here. So this is my 60 degrees. If I want to draw it in the sketch here, I can. So when I try to figure out the values for my x and my y, I'm going to have the hypotenuse of 10. This down here is going to be 10 times the cosine of 60 degrees. And this one here is going to be 10 times the sine of 60 degrees. If I plug those values in, I can figure out my x and y component. So I'll figure out the x first, so I'm going to do 10 times the cosine of 60. And this gives me a value of 5. And I know that this is a positive 5 because this is the base, and this is the tail, and this is the tip of the vector, so things are going up and to the right. So the x component is going to the right, which means it's a positive. And then I'm going to do 10 times the sine of 60. So this is my vertical component, and this is going to be approximately 8.66 from the looks of it. And this again is also positive because we're going to the right and then we're going up. So that would be the x and the y component for vector A. Vector B says it has a magnitude of 5 and it's at a degree of 90 from north. So it's kind of interesting here. We do not necessarily have to draw a triangle because the vector itself is on the horizontal. So there is no vertical component to this vector. It just has a magnitude of 5 and it's at 90 degrees. So magnitude is 5, going to the right. Degrees from horizontal here is actually 0 because it is not above or below the horizontal, it's on the horizontal. The x component is the horizontal, which is obviously going to the right, so that's a positive 5. And then the y component is non-existent because it does not go up or down. So if something's perfectly vertical or perfectly horizontal, you don't really have to draw a triangle because your x or your y component, one or the other, is actually 0. So no need to use trigonometry. So we lucked out on that one. Letter C, vector C, says it has a magnitude of 8 and a bearing of 225 degrees. So I know that the magnitude of it's 8. And 225, again, we got to think a little bit. Straight up and down is 0, straight to the right is 90, straight down is 180, and straight to the left is 270. So I know that this one will be pointed somewhere in this direction. So it's going to go down, and then it's going to go to the left. So again, 180 here, what do I need to add to 180 to get to 225? Means I would have to add 45 degrees. And you may ask, well, why am I labeling this angle? Because if the horizontal is here and you're rotating from 0, it goes 0, 90, 180, and 225. So if this was the start, it's got to rotate this way. So this angle is 45. By deductive reasoning, I can know that this angle is also 45. So this is my x and this is my y. It depends what angle I'm going to use. Here, it really doesn't matter because both the angles are the same. For example, if I was using this, this would be my opposite side and this would be my adjacent side. Where if I'm using this angle, this is my opposite side and this is my adjacent side. Here, again, if the angles are the same, it isn't going to matter, but if this angle was, say, 30 degrees and this one was 60, if I was going to be using 30, my opposite side would be my x and my adjacent side would be my y. So it's a little different than what we did up above. Either way, I'll just continue using this angle here, so we keep our horizontals the same. So if you do the sine or the cosine of 45, you get the same value, so this really isn't going to change anything. So I can do this, I can do 8 times the cosine of 45, and here I can do 8 times the sine of 45. And then we'll plug in the values here and see what we get. So 45 degrees from the horizontal, I'm going to do 8 times the sine of 45. This gives me 5.65, and I'll get the same thing for y. Now the thing to notice here, before I write in 5.65 for the value of x or y, y goes down and x goes to the left. So in terms of ordered pairs, if this was the origin, which is where the tail of the vector originated from, it's going to the left and it's going down, or it's going down and it's going to the left. Either way, the x value is negative and the y value is negative. So when I write in this 565, this needs to be a negative 565 and a negative 565. Now, I'm going to sum up the components from up above. You would do the same process here if we had 5 vectors or 20 vectors. The only ones we can directly add together are the x's and the y's because they're the only ones that are collinear. They're the only ones pointed in the same direction. So I'm going to go through and basically do that. So I have 5 plus 5, which is 10, and then if I subtract the 565 from the 10, this leaves me with a positive 4.35 for our x component. And then our y component, we have that 8.66 that we started with. Add 0 and subtract 565, and that gives me a positive 301. These are the components I'm going to use to draw my new triangle to solve for the resultant vector of a plus b plus c, which is going to equal d. So in order to do this now, I'm going to draw a new triangle. My x is equal to 435, and my y going this way is equal to 301. And since these are both positive, I know that my vector goes in this direction. So this is vector d. We'll call it d of r. We still need to figure out the magnitude of it, and we want to figure out theta. So to figure out theta, the only information I'm given right now is my opposite side and my adjacent side, which is going to be my y and my x. So the tangent function talks about the difference between tangent function is opposite over adjacent. So if I want to solve for the theta, I got to do the inverse tangent of O divided by A. And if this is my corner, opposite is here and adjacent is here. So this is going to be 3.01 divided by 4.35. And plug in this value, and this is going to tell me what my degree is from horizontal. So inverse tangent, you got to find the tangent to the -1. You got to do 301 and 435 divided out in parentheses because that whole value needs to be isolated. And now my theta is equal to 34.68. So there's the degrees from horizontal. And then how do we figure out the magnitude of this? We have multiple choices. The most basic concept I would try to tell people is just stick to Pythagorean's theorem, if that's what you're comfortable with. So the 435 squared plus the 301 squared, if I square root that, that should tell me the value for d of r, or the magnitude for that hypotenuse. So I'm going to do 432 squared plus 3.01 squared, and then I'm going to take the square root of that value, and I get 5.29 approximately. So that'll go here, which will also go here. And then the last bit of information that they give us is they want us to figure out what is the degree from north. Well, we got 34.68 degrees here. And if you remember, north is up here at 0 degrees, and this is at 90 degrees over here. So you can do 90 minus the 34.68. And that should tell you the degrees from north. So this is at about 55.32 degrees from north. If you guys have questions, feel free to ask. This stuff is not easy, but if you work through it and follow the process and steps, I think it'll be good. So please attempt all of the practice problems and quizzes, and there's going to be alternate resources out there for you in addition. Otherwise, feel free to email or contact me, and we'll try to figure these out as we go. Appreciate it. Thank you very much, and you guys have a good week.